Thank you very much. Really grateful to be able to present here. My name is Paco Nathan. I'm from Databricks. We're the people behind Spark. And a little bit from my background, I have a dual background, really, in, on the one hand, on distributed systems, working with big data frameworks, for instance. On the other hand, with machine learning, more towards the use cases. And I had led teams, effectively data science teams, for a number of years, working on very large-scale machine learning in industry. For the past few years, I've been working as an O'Reilly author and working with different open source projects, such as Spark. So what I wanted to present was, just briefly here, as a prelude to the tutorial tomorrow, give a bit of context for where did big data come from, and how does Spark fit into this, and what some of the trajectory is, and how that has impact on the kind of research that you're doing, or how this can be used for the kind of research you're doing. So in terms of some history, big data really traces back to about the late 1990s. I would put it at about Q3 of 1997. There were some teams, just to pinpoint it. There were 4 teams working at the time, though, which were out in e-commerce, and they were facing a very similar problem, that if you were going to scale up a web app on the internet, you're probably going to pay a lot of money to Sun, Oracle, maybe IBM, to build bigger and bigger servers for you, and then get bigger and bigger Oracle licenses. And so these 4 teams all happened upon the same strategy, namely Greg Linden's team at Amazon, Randy Shup's team at eBay, Eric Brewer's team at Tomy, which became Yahoo Search, and Larry and Sergey were at Stanford, but they rolled out as Google just shortly after. And the idea was that they would take the workloads that they had and parallelize them and be able to run them on commodity hardware running Linux primarily. eBay was still back on .NET, but it moved to Linux. So the idea was to move away from this mainframe kind of worldview into more of horizontal scale out on commodity hardware. And what this set up was a kind of virtuous cycle, because this is really the epigenesis for machine data. Prior to this point, if you were looking on the internet at different web pages, the data that's represented had most likely been put there by a person. It might be coming out of a database, but somebody had put the data into the database. After this point, though, it's a real inflection point, because after this, you see this huge uptick in data that's been collected by machines, primarily log files. So what happened was that you had these big e-commerce web apps, and they were capturing social interaction in terms of machine data, log files. And then the log files were being aggregated and fed into machine learning, which was then creating data products to make the web apps smarter, to make the interaction more effective. So you get this kind of virtuous cycle where you get more and more data collected, more and more data products feeding back in, and a lot more horizontal scale out. So that's why I can really pinpoint this. Actually, if you want to read some of the case studies, I just spent a week in Brazil at a conference with Randy Shup, who did this for eBay, and he documented it pretty well. Like Greg Linden also has done a pretty good job. So yes, very specific. Google was, of course, one of the big winners for this kind of scenario, and they built out machine learning workloads at scale, doing PageRank and things for search. The problem that they had was, if you're just rolling up a log file, that's relatively trivial. But if you have a complex machine learning workload that requires, say, 2,000 servers, and it has to run for hours at a time, the probability of a large chunk of those servers dying while you're processing is actually quite high. And even today, with a 2,000 node cluster, you get a probability average failure rate of 10 servers per day dying. Of course, back in 2002, it was a lot higher. And it's largely because the spinny disks fail. And so Google had this problem that you could restart the workloads, the critical workloads, but you had approaching 0 probability of completing the workloads if you followed that. So it was about risk. It was about managing risk. So they built out 2 layers. One was something called GFS, Google File System, and the other was MapReduce on top of that. And how many people have ever read the MapReduce paper? Anybody here? Okay, great. So in the first paragraph, they make a big deal about functional programming and how really what they did was they went back to the 1930s, some of the math that had been done for lambda calculus and for combinators, et cetera, and they taken a cue from there and implemented a couple of the combinator patterns, map and reduce, to be able to leverage some fault tolerance. And this moved right along. So I just want to show a timeline of where Spark fits in. Google did this work in 2002, 2003, published in 2004, and then there was the Nudge project, building open source web crawlers, picked up in this paper, implemented it as open source, 2005, 2006. Yahoo sponsored it. A couple years later, it becomes a big conference. And suddenly, everybody's adopting Hadoop, and Oracle and IBM and all these others are jumping in. And right at about that time, I had a friend who had been working at Google, and he'd been working on cluster management, and Google higher-ups told him that they already had a solution like this. And so he moved on, and he went to go do his PhD at Berkeley, along with some of his friends. It was something called the RAD Lab. It was later named AMP Lab, and VMware, Google, Amazon, and others sponsored it. But basically, they were looking at distributed systems. And a lot of these grad students were interning at places like Facebook and Cloudera and Google and whatnot, and they were seeing how, even given this big uptake of Hadoop, it really wasn't fitting a lot of the cases. So in 2009, Matei Zaharia built sort of a proof of concept on top of the main project they were working on called Mesos. He built a proof of concept in Scala called Spark to show how could you move beyond Hadoop. And that picked up. It was pushed up in source in 2010, and by 2014, it became a top-level project at Apache. I'll show some growth curves. It's been exponential growth, quite literally. Now, the thing about this is that the hardware that Google was working with back here, that was a decade ago. And when you think about what's happened in commodity hardware over this decade, there's been a dramatic evolution of it. Back here, they were worried about disks failing. But out here, we've got gigabit networks, we've got SSDs, we've got multi-core, huge memory spaces. We've got a completely different generation, a decade later, of hardware to leverage. And MapReduce didn't have that and wasn't trying to address it. So a lot of what this represents out here is really a generational shift a decade later. So I'll cut through this. I've got some links in here. We'll go over this more tomorrow, but a lot has changed. The spinny disks, we've kind of nailed that problem. The curves have really flattened out on that. We have other problems to deal with now with distributed systems. So there are really two problems we were talking about in terms of Hadoop, and that this team saw back at Berkeley, back circa 2009. One was it's very hard to find programmers who can think directly in terms of maps and reduces, especially for complex workflows. And I used to lead those teams, and it was really hard to hire people to do it. The other thing is that there are very substantial performance bottlenecks when you try to do this at scale. And we'll go through some scenarios about that tomorrow as well. So as a result, people followed a strategy to build out specialized systems. And the strategy is Google publishes a paper, and then people make an open source version of it. So there was the Prelude paper about graph computation, and then the open source giraffe. The Dremel paper about nested tuples, and the open source drill. The F1 SQL at scale paper, and then Impala. The Millwall paper about streaming, and then, of course, S4 and Storm, et cetera. So people built out a lot of specialized things based off of some really great papers from Google. And there's a cost to that. It requires a lot of machines. It requires a lot of learning curve. It also induces a lot of latency. And so if you think about having to bring in your data in one cluster, process it slightly, move it to another cluster, move it to another cluster, et cetera, you've got all this wire tax that you're paying. And in some types of use cases, you can see degradation of value within milliseconds. So hopping around between clusters is actually quite a bad thing. So Spark was really looking at this, trying to come up with a unified engine to be able to consolidate a lot of these different types of specialized systems and put them into a common framework. And here's the original papers on this. I know it's kind of clipped down here, but I'll post it. And the idea was to apply some working set theory and an abstraction called an RDD, which is essentially just a distributed collection of data to which you can apply functions. And so the general category for this in terms of functional programming is called an applicative system. For those of you who've worked with R, you've seen applicative systems a whole lot. But again, it's the idea that you have an array or a matrix of data, and you apply a lot of functions to it, chain them all together to be able to express a complex workflow. And it's really taken off. Come on here. There are really two changes, if you've heard about Hadoop, there are really two changes that need to happen to make this take off. One was we had a different generation of hardware, so we needed to come up with better ways to leverage it and come up with better, more generalized ways to share data effectively, leverage the caching. Number two, there was a project at Microsoft Research called Dryad Link, which looked into representing complex workloads in big data as directed acyclic graphs, and then being able to apply graph reduction techniques, other optimization techniques, to be able to make this run better. Microsoft, for obscure reasons, canceled the project, but it helped to inform a lot of other open source, such as Spark. And so what this represents, and again, we'll go over this in more detail tomorrow, but there's the core engine, and there's this notion of an RDD, a collection of data to which you can apply functions. And that gives you parallelism, fault tolerance, and the ability to optimize. And then on top of that, we can take this same abstraction and make a one-to-one correspondence between tables in SQL and an RDD. And then the result sets from SQL queries are also RDDs. So since we can make that logical correspondence, we can just basically map the SQL down there and run it fast. Same thing with streaming. We can take and use a micro-batch strategy. We were just talking about streaming, and that was a fantastic project too. I want to dig in more on what New York Times says. In streaming, what we can do is establish time windows from 500 milliseconds and up, where any data that comes in on the receivers during that time window is considered a collection of data, and we apply functions to it, just like we do throughout the rest of Spark. With machine learning, we can say that we can take the vectors that we would be using to train algorithms or to test algorithms, possibly sparse vectors or matrices if they are, and represent those as RDDs. And so you have the same abstraction being used for machine learning. And then with graphs, we can say that we can take an RDD of nodes and then an RDD of the connections between the nodes to be able to define a graph, compose those together, and then again apply functions to them, and the results of the graph algorithms are themselves RDDs. So on and on, we've built out different types of abstractions so that instead of having 5 different clusters, you can pull this all into one app and then roll that out on one cluster. It turns out it's a very powerful abstraction. There's integration with Java, Python, Scala, also Clojure, SQL, and now R. And it really does, when you look at this, it represents a higher level of abstraction than what we had with big data tools before. There was an initiative in about late 2007 to build abstraction layers on top of Hadoop. Cascading, Pig, Hive, et cetera, came out after that. But they're still using the same maps and reduces underneath. And so by relaxing some of the constraints at the lower level and then building out better abstractions at a higher level, we're able to come up with much faster programs. And so kind of proof in the pudding here, if you look at the word count, which is sort of a canary in a coal mine program for big data, if you look at word count for Hadoop, it's 53 lines of unapologetic Java. And it looks a lot like enterprise Java beans, for those of you who ever did EJBs. But if you look at the same program done in functional programming in Spark, it's 3 lines of code. And so there's a real software engineering issue there, that if I'm managing a team that has responsibility for a lot of apps, if I can reduce my code volume by an order of magnitude, number 1, I have much lower probability of bugs, number 2, much less maintenance cost, and number 3, when I have to go look at my code 6 months after I've written it, I might be able to actually understand it. So big cost there, big improvements there. One of the other things I mentioned about inheriting some research from Microsoft, there's a notion of a DAG, a directed acyclic graph. So we can specify that we have different collections of data and different functions applied to transform them, including maybe shuffles and joins and whatnot, very complex kinds of transformations. We can take this graph and we can decompose it into what we call stages, which can then run in parallel or maybe have a synchronization point where they don't. But we understand the graph in terms of what stages need to be run. And then we can apply graph reduction techniques to optimize those, possibly move predicates around, use some sort of invariance, use push down into other data frameworks, et cetera. But a lot of the tricks that you would see in a SQL engine can be applied directly here. And again, proof in the pudding, the Spark team recently set the world record. There's something called the gray sort, the Daytona gray sort. Yahoo had held this record before. They had done it with approximately 2,000 servers in a cluster. And the Spark team was able to take this and run it 3 times faster with 1/10 the size of the cluster, approximately 200 nodes. And if you look at the metrics across the board, it's about a 30x improvement. Yahoo didn't actually publish what kind of hardware they were using, but it was dedicated, whereas this was all entirely published open, and it was done in AWS. It was done in the cloud, so it's repeatable. Also, just if you look, there's this inflection point in late 2013, like Q4 of 2013, where most of the metrics that we're measuring, it just takes off. It goes hockey stick. So it's been quite an interesting it is the most active big data project on Apache now. Also, O'Reilly. I do a lot of work with O'Reilly, and I work specifically on the Strata conference, and I encourage everybody to come to Strata. But O'Reilly did some data science work recently and showed that the highest median salaries in big data are, of course, with Spark. And an even more rigorous study here was from TypeSafe, where they looked across the board at a large sample in terms of what people are using in industry, what languages, what kinds of use cases, et cetera. I would highly recommend. There's a very strong community for this, a number of different resources. I'll publish these slides, but a lot of great links to learn more or to talk more with people. And of course, we'll be having the tutorial tomorrow. And and some MOOCs are coming up too. In a couple of months out of UCLA and Berkeley on edX, two of the professors that have been associated with Databricks and Spark are going to be doing this. Anthony Joseph at Berkeley and Amit Talwalkar at UCLA. And we have our own conference too coming up in San Francisco. And thank you very much.
You showed the MapReduce program for word count. Have you tried the Google Cloud Dataflow? How many lines would that be?
Dataflow is a similar category, again, using this notion of a DAG.
So the next question will be, how does that compare to the Spark framework?
Yeah, no, that's a great question. I got to spend some time with the Dataflow, some of the Dataflow team, end of last year at a conference when we were over in Europe together. And it is a very comparable approach for certain use cases. The thing that constrains Dataflow is that it doesn't handle the breadth that Spark has. So whereas we're going after SQL, we're going after different machine learning algorithms at scale. In parallel, we're going after the streaming, we're going after graph, et cetera. Dataflow is more constrained.
They also have streaming. Is that in the same system? Based on your knowledge, is that the Google Cloud Dataflow streaming and the sort of batch processing, are they integrated in the same system in one engine?
I don't know exactly about. I mean, I should check that more. I mean, that's the big takeaway that I had on the difference was here you could combine different use cases, come in with a common app. With that one, there was more integration, but it was very nice integration with what they had on their cloud offering, which I think is actually quite good.
So is the first statement is a subset of the features of Spark?
Roughly. I would get in trouble if I did that unqualified, but I mean, it's definitely going after a lot of the same kind of use cases, so definitely there.
Is the technology largely based on Java?
No.
Do you see a lot of people using big data frameworks that don't really need them? And sort of how do you think about that problem these days? Because a lot of, even in science and just in general, like the world hasn't actually, in a lot of ways, the world hasn't changed in the last 10 years, but computers have changed a lot. No. And you can fit all kinds of things, under your desktop now that you couldn't 10 years ago. And, everyone wants to use the cool frameworks, but what if you just, bought 500 gigs of RAM and wrote your thing in C?
Well, that's a great point. Okay, so 3 quick questions to kind of bracket that. Number one, I definitely, I had a team that was a case study for Elastic MapReduce on Amazon. And so we worked very closely before that was pushed public and then worked with it afterwards. And I've seen a lot of companies, I've been rolled out to be a reference company, a reference customer for a lot of companies being pitched on using Hadoop. And then I've also seen a lot of these companies that, maybe they had hundreds of gigabytes. At the end of the day, they didn't need Hadoop. And so they rolled back and used something like Redshift in the cloud instead. So there's definitely those use cases. That's on one end of it. On the other end of it, in the middle, let's say, what you brought up, the fact that we're seeing a generation later of hardware, it has multi-core, it has so much RAM on it, you can't actually fit it in one JVM without a lot of garbage collection. So yes, we are seeing this kind of convergence where a lot of use cases more and more will fit on a single server for a while. But what's very telling is when you go out and look in the industry, and particularly I think here in terms of, I'm seeing a lot of genomics and life sciences also with the equivalent argument, a lot of the data has been ignored because it was so intractable. I mean, if you go to GE and you look at the sensors, the rotational bearing analysis sensors they have in flight on commercial aircraft, the amount of data that's coming off of aircraft in flight is 12 exabytes per day. And I was actually working with some people who had the contract with GE, and GE said, hey, can you help us put that in the cloud? You can't put 12 exabytes a day in the cloud. That's not possible. So I mean, there's a lot of these use cases that actually are very, very salient. We would love to be able to get that rotational analysis because there are multi-billion-dollar supply chains. If you ground an aircraft and take its engine off, you have to ship it somewhere. There are great industrial uses for a lot of data that has frankly been ignored for too long, largely because of the data rates, mostly because of real-time and streaming. And I think that's another driver I didn't really mention strongly enough. What we're seeing across the board is batch was great, Hadoop was interesting for batch, a lot of low-hanging fruit there, but industry and science both need more and more real-time to get something effective done. And that's going to kill the argument of let's put it on a single server.